Hello and welcome everyone. So let's start off with this here. This is a little problem. I'd like you to, again, pause the video, stop it here, and try this one on your own. And again, there's no need to write a proof for this problem here. We're just looking at a demonstration of this here. So we have a parallelogram ABCD. We're given this information. We want to show it's a rhombus. Okay, that seems pretty fair. So we're going to go ahead and sketch this here. So ABCD kind of looks like this here. I don't know if it's a rhombus or not, but we can go ahead and sketch that here. Here's A, B, C, D here. So we have AB is 2x minus 1, DC appears to be 3x minus 10, and AD is x plus 8 here. All right, that seems fair. So we note that in this situation here, we have ourselves a parallelogram. And as I'm sure you recall, one of the properties of a parallelogram, is that the opposite sides are congruent here, right? So we can say the opposite sides of a parallelogram are congruent, right? So as a result, we can now set up here that AB equals DC here. So 2x minus 1 equals 3x minus 10 here. So we can go ahead and set that up. That's pretty straightforward here. We get negative x. I think we can add 1 to both sides here. We get negative x, I believe, is negative 9. So divide by negative 1 here. That works out. We get x equals 9. Now, of course, we can go back and finish this off here. So now we know that x equals 9. So now we can go ahead and substitute this in. These two should be the same, which makes sense here because you have 2 times 9 minus 1, which I believe is 17 here. Similarly, we have 3 times 9, which is 27, minus 10, which is 17 as well. So you have a 17 here. Now, they gave us AD, so we might as well go ahead. We get 9 plus 8 here, which is 17 as well. Okay, so wait a minute. I mean, should be sufficient information here, right? Because I've got a parallelogram and we have consecutive sides being congruent. So that means this is guaranteed to be a rhombus here. And of course, if you really wanted to be sure about this here, this 17 could also go on the opposite side. And then bang, you have 4 congruent sides here. So it's guaranteed to be a rhombus. So that's the nice part about this here. Okay, so that works out very, very nicely here. In this situation, you kind of have this. So notice that, this is a picture of our object here. This is a rhombus. Now, of course, the problem doesn't tell us anything about the angles of said rhombus here. So, our rhombus could look something like this, or, we can set the angles to some, value that we want here. So, for instance, if I insist, say, that this angle is a 90-degree angle down here, and here's 17, 17, 17, 17, we can show, wait a minute, this is a parallelogram here, we have a right angle, so it's going to be a rectangle as well. That means angle C is a right angle, so there's a right angle over here because these are consecutive angles, so they're 90 degrees, so this is also 90 degrees as well. And I've got myself, probably one of the simplest quadrilaterals out there, and one of the most well-known, the square. So with that in mind, ladies and gentlemen, let's take a look at this here. So there are actually quite a few definitions for the square here, and both these definitions are perfectly valid. Depending on the book that you're looking at here, or depending on the thing, you can actually determine the definition of square like this here. So we can say, for instance, a quadrilateral is a square if and only if it's a rectangle with congruent consecutive sides. Similarly, we can say that a quadrilateral is a square if and only if it's a rhombus with a right angle here. So that's going to be very important to us as we go, okay? And we can kind of see this sort of thing here. This works out very nicely. Now, the nice part about the square is that the square has properties of pretty much everything here. Given the fact that it's a quadrilateral, a rectangle and a rhombus here, we know, therefore, that the square should have all these properties here, right? So the square should have the properties of the rhombus and should have the properties of the rectangle. And the nice part about this is that we can actually start relating these objects together. So, what I'm going to do now is we're going to look at, try to put these together based on sort of the properties of the objects here. So we're going to create sort of a family tree, so to speak. Something like a family tree from, something that you would see, for instance, on one of those family ancestry sites. Or we can do something similar to what they do in biology for evolutionary biology. And you kind of have this phylogenetic tree, so to speak. So, we can start off with our quadrilaterals here at the very beginning. This is sort of our ancestral object here. This is going to be what we're going to be looking at the very beginning. And as we go down here, right, we want this to become more specific. And this ties into our analogy to that of the of an evolutionary tree in biology here, okay? So considering what we have with the quadrilaterals here, right, we can go ahead, we note that a parallelogram, right, we know it's a specific type of quadrilateral here. Not every quadrilateral will be a parallelogram, so we can kind of think of it as a more specific type of quadrilateral. So I can kind of do something like this here. So we have our parallelograms like this here. I think you can see that's going on. Now, if you recall, we also have our square, we also have our rectangle and our rhombus and our square, so we can go ahead and put this in here. Now, according to our definition, if you recall, right, a rectangle is a specific type of parallelogram here. So now I can kind of do something like this here. So we know that they actually both branch off from parallelograms here. We can actually be more specific here. There were specific types. So we have ourselves here our rhombuses, right, our rhombuses here. And we have our rectangles here. Okay, that seems pretty good here. Now, noting for our square, it makes sense since the square has the properties of both a rectangle and a rhombus, it should look something like this here. So it makes sense, therefore, that our squares should be at the bottom of our tree here. It's the most specific type of quadrilateral, and it'll look something like this here. So that means, if you think about this, if you think about this in terms of a evolutionary tree, we start off with sort of this, progenitor organism here, and then we go down to something a little bit more specific, and then and here it kind of branches off here, only to re-evolve back together. No biologist, but this seems a little bit unnatural. Maybe my colleagues in the biology department can help me out with this one here. I can't really think of an example of something like this. I've heard this term of convergent evolution before, but I don't know if this applies here. Now, if you remember our other analogy of the family tree, this is even worse, right? Because you have your progenitor, your ancestor here, or your matriarch, patriarch, and then you have descendant here, and you have a descendant here of that person, and then you have two descendants here, and then, well, yeah, I'm going to let you make your own joke here. I'd rather not say.